Okay, so continuing with our third video in 6.3. So for example, let's solve the following using identities. So solve the following using identities. Identities. Okay, so number one, let's say we have 6 times sine squared theta minus 6 times cosine squared theta is equal to 3 times the square root of 3. Okay, so pardon me. So we have 6 sine squared theta minus 6 cosine squared theta is equal to 3 times the square root of 3. So the first thing I'm going to do is I'm going to divide by 6, everything by 6. In fact, maybe I'll divide everything by negative 6. You don't have to do that, I just know what's coming. Okay, so what do I get then? I would get negative sine squared theta positive cosine squared theta is equal to negative root 3 over 2. Okay, so let me rewrite the left-hand side as cosine squared theta minus sine squared theta is equal to negative root 3 over 2, because that is the identity for cosine of 2 theta. So this is cosine of 2 theta on the left is equal to negative root 3 over 2. Okay, so I'm going to rewrite the angle 2 theta in purple. So at what angles 2 theta is cosine, the x-coordinate, negative root 3 over 2, and I claim that that's 5 pi over 6 plus 2 pi k, and it's also 7 pi over 6 plus 2 pi k, where k is an integer. However, I need to divide by 2, right? I'm solving for theta, not 2 times theta. Okay, so what do we get when all is said and done? Let me just move this up here. We get that theta will be 5 pi over 12 plus pi k, 7 pi over 12 plus pi k, where k is an integer. So that's infinitely many solutions to that one. Okay, so number 2, these are getting a bit long here, so bear with me. We've only got 2 more problems. So number 2, let's say we have 4 times sine squared theta minus 3 times sine of theta plus cosine of 2 theta is equal to 0. So let me rewrite this. So we have 4 sine squared theta minus 3 sine theta plus, actually I should have color-coded. Let me color-code this. Cosine 2 theta is equal to 0, because I'm going to rewrite cosine of 2 theta. I'm going to rewrite it using his double angle identity. So it's going to be cosine squared theta minus sine squared theta, what I had above, right? The double angle formula for cosine, one of the 3. Okay, so now I can combine like terms. So I end up with 3 sine squared thetas when I combine like terms. Sine squared thetas minus 3 sine thetas plus cosine squared theta. And I forgot to write theta. Shame on me. That's minus points. Points off for not writing theta. Okay. Okay, so plus cosine squared theta is equal to 0. Well, I know I would like to get rid of cosine squared. And cosine squared, of course, is... Actually, let me keep this in orange. Cosine squared is 1 minus sine squared, so I can do that. So let's rewrite all of this. copy, paste, but I'm going to rewrite cosine squared as 1 minus sine squared theta from my main Pythagorean identity. So let me indicate where I'm getting that from. Semicolon, because we have cosine squared theta plus sine squared theta is equal to 1, right? Hence, cosine squared theta is 1 minus sine squared theta. So now once again, I can combine like terms, leaving me with 2 sine squared thetas minus 3 sine thetas plus 1 is equal to 0. So this now is going to require a u substitution. So I'm going to let u be equal to sine of theta. So what I get then is 2 u squared minus 3 times u plus 1 is 0. Okay, so now I'm looking for 2 integers that have a product of 2 times 1 is 2, and they add to negative 3. So that's going to be, how about negative 2 and negative 1? They add to negative 3, but they multiply. So I can rewrite this as 2u squared. Actually, maybe I'll keep that hot pink. What the heck? So 2u squared. Let's do now minus 2 u's. Then minus 1 u plus 1 is equal to 0, and now I can factor by grouping. So from the first 2, I see that I have a 2 and a u common. And when I factor that out, I get a u minus 1 remaining. From the second grouping, it looks like I have a minus 1. When I factor that out, I have a positive u and a negative 1 remaining. Okay, each of these now has a common u minus 1, which when I factor out leaves me with a 2u minus 1. Is that equal to 0? But remember, u was a placeholder for sine. So this is really sine theta minus 1 times 2 sine theta minus 1 is equal to 0. So in the first case, if I have that sine of theta minus 1 is equal to 0, using the 0 factor property, that means that sine of theta is 1. And let me rewrite theta in terms of purple. Okay, so at what angle, plural, is the y-coordinate 1? Well, that's pi over 2 plus any integer multiple of a full revolution. So let's do the same analysis over here. So we have 2 sine of theta minus 1 equals to 0, which means that 2 sine of theta is equal to 1, which means that sine of theta is 1/2. And once again, let me rewrite theta in hot pink here. Okay, so at what angles is sine, the y-coordinate, 1/2? That's pi over 6 plus any integer multiple of a full revolution, and 5 pi over 6 plus any integer multiple of a full revolution. So writing the entire solutions, so theta will be, from smallest to largest, let's do pi over 6 plus 2 pi k, then pi over 2 plus 2 pi k, then 5 pi over 6 plus 2 pi k, where k is any integer. And I don't like that integer symbol. Let me write that better. Okay, there we are. So those are the infinitely many solutions to that problem. Okay, we've got one more problem, which of course is going to go off this page, but that's okay. So number 3, let's solve 1 minus 3 sine of 2 theta plus cosine squared of 2 theta is equal to 0. Okay, so what color did I use? Okay, I'm going to use color. Yeah, I should use orange for this one. Okay, so I have 1 minus 3 sine of 2 theta plus cosine squared of 2 theta is equal to 0. So I'm going to rewrite cosine squared using my main Pythagorean identity. I know that cosine squared is 1 minus sine squared of whatever the angle is. So this is 1 minus sine squared of the full angle 2 theta. So what I've done here is I've used my main Pythagorean identity. So this would be cosine squared 2 theta plus sine squared 2 theta is equal to 1. Okay, so now I can combine like terms. So negative 3, oh wait, no, I have no like terms. The only one I have is 1 plus 1. Okay, so I have 2 minus 3 sine theta, sine 2 theta, minus sine squared 2 theta is equal to 0. So I'm going to rewrite this. I'm going to move everything to the right-hand side. So I'll have 0 as positive sine squared 2 theta plus 3 sine 2 theta minus 2. Okay, so I could do another u substitution here if you guys need it. Maybe we'll do that. So let's let u be in place of sine theta. So now I can rewrite this as 0 is equal to u squared plus 3u. Actually, what am I saying? It should be sine of 2 theta, shouldn't it? Not sine of theta. Sine of 2 theta. Please tell me I didn't make a silly mistake like that up here. No, okay. Okay, minus 2. Okay, so this should be fairly straightforward to factor. What two integers have a product of negative 2 and a sum of positive 3? Well, yeah, they add to 3 and have a product of negative 2. Did I do something wrong here? U squared. Okay, so u is equal to negative b plus or minus the square root of b squared minus 4ac. Oh, that's why. All over 2a. Wow, I really made these miserable numbers, didn't I? I wanted to make them good numbers, but I failed. What did I do? Do you know what? I don't want to deal with ugly numbers. So I'm going to manipulate this backwards so that it works. So I would like this to be a positive 2. So how can I go about that? Making that a positive 2. So this would have to be a negative 2 here, which would mean that this 1, in order to add 1, would have to be a negative 3. Okay, so let's make that a negative 3. Does that work? So negative 3. Negative 3, this is called cheating. This is called working backwards to get what I want. Okay, so that works. Now the numbers work out nicely without a square root of 17. Okay, so if I make that a positive 2, then I just get plus 1 plus 2, which is a lot simpler. Okay. Note, cheating allowed when you're an instructor. Okay. So let's replace u with sine of 2 theta plus 1 and sine of 2 theta plus 2. So we have that either the first sine of 2 theta plus 1 is 0, plus 1 is 0, or, which is interesting, and you'll see why in a moment, we have that sine of 2 theta plus 2 is 0. Okay, so on the left-hand side, I have that sine of 2 theta, and let me put 2 theta in purple, is negative 1. So at what angles is sine negative 1? Well, that's 3 pi over 2, plus any integer multiple of a full revolution. But I don't want to solve for 2 theta. I want to solve for theta, so let's divide by 2. So I get that theta will be 3 pi over 4 plus pi k, where k is an integer. And actually that'll be it, because let's look at this. Sine of 2 theta is negative 2. Well, that's impossible, because sine is bound between positive 1 and negative 1. So this does not exist. That's outside of the range. So therefore, my solution is just these infinitely many solutions. Okay, so that is it for section 6.3.